Hello everyone. Today we will study normal distribution. Before I introduce what it is, let me first of all show you an example here. The exam score of 30 students are listed below. Draw a histogram using class intervals from 0 to 10, 10 to 20, and so on. So let me first of all show you how to draw a histogram. Before we draw a histogram, let's first of all draw a frequency table. Before histogram, let's first of all draw a frequency table. Let's draw a frequency table first. Then, based on the frequency table, we draw a histogram. In the frequency table, in the first row, we put a class interval in the first row. The class interval here is from 0 to 10, but the thing is, the data value starts from 36. The data value starts from 36. So our first class interval is from 30 to 40. Because the data value starts from 36. Our first class interval is from 30 to 40. We don't start from 0. But it's the same format. It must be the same format. From 30 to 40. 30 is included. 40 is not included. That interval is from 40 to 50. 40 is included, but 50 is not included. Next is from 50 to 60. Next is from 60 to 70. '70 to 80. '80 to 90. And no one scored more than 90, so we can stop here. We don't need to draw 90 to 99, 90 to 100. No one scored above 90, so we draw 80 to 90. That's the last one. That's the first row. Put a class interval in the first row. In the second row, write frequency. In the second row, write frequency. Let's count. How many students score between 30 and 40? There's only one. So the frequency is 1. The frequency in this class interval is 1. Now let's count. How many students score between 40 and 50? Here we found 2 here. So the frequency in this interval is 2. Next, let's count. How many students score between 50 and 60? 1, 2, 3, 4, 5, 6, 7, 8. 60 is not included here. So 1, 2, 3, 4, 5, 6, 7, 8. Next, let's count. How many students score between 60 and 70? 70 is not included. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the frequency in this interval is 12. 12 students score between 60 and 70. Next, let's count how many students score between 70 and 80. 80 is not included. 1, 2, 3, 4, 5, 6. So frequency in this interval is 6. Next, let's count how many students score between 80 and 90. There's only 1. So the frequency in this class interval is 1. That's the frequency table. Next, based on the frequency table, we can draw a histogram. Histogram looks like this. It looks like a connected bars. We use connected bars to represent frequency. For histogram, we use connected bars to represent frequency. For histogram, we use vertical axis to represent frequency. For histogram, we use vertical axis to represent frequency. And we use horizontal axis to represent exam scores. In this problem, the data values are exam scores. So we use horizontal axis to represent exam scores. Here, first interval is from 30 to 40. So intersection here is 0. If we try to draw 30, let's draw a little break here. Let's draw a little break here. Say 30 is here. 30, 40 is here. 50 is here. 60 is here. 70 is here. 80 is here. 90 is here. Then, in the first class interval, the frequency is 1. We draw a bar whose height is 1. So, 2, 3, 4, 5, 6. Let's say 2 is here. 4 is here. 6 is here. 8 is here. 10 is here. 12 is here. So, in the interval from 30 to 40, draw a bar whose height is 1. Next, in the second interval, frequency is 2. We draw a bar whose height is 2. Next interval, frequency is A, so draw a bar whose height is A. Those bars must be connected. Those bars must be connected in histogram. Those bars must be connected. Next interval from 60 to 70, we draw a bar whose height is 12. Next interval, frequency is 6. So we draw a bar whose height is 6. Next interval, frequency is 1. So draw a bar whose height is 1. This is the histogram of the exam scores. But by the way, what I did here is not the formal way to draw a histogram. I tried to make the problem simpler, so I draw the histogram in an informal way. In the future, when you move to the higher level statistics class, you'll learn how to draw a histogram in a formal way. Now let's observe this histogram here. In this histogram, we can see that there are more data values near around the center. Fewer data values are far away from center. In general, in a data set, if its histogram has more data values near around the center, fewer data values far away from the center, and the histogram tend to have an upside down bell shape. Upside down bell shape looks like this. Let's call upside down bell shape. That's an upside down bell shape. In a data set, if the histogram has more data value near around center, fewer data values far away from center, and the histogram tend to have an upside down bell shape, then we say the data set has approximately a normal distribution. If there are more data values near around center, fewer data values are far away from center, and the histogram tends to have an upside down bell shape, then we say the data set are approximately normally distributed. Next, let me introduce normal distribution. Consider a very, very large data set. Consider a very, very large data set with n real numbers. where each real number in the dataset is called data value. Each real number in the dataset is called data value. The real numbers in the dataset, they are called data values. As n tends to infinity, as n tends to infinity, and the class width in the histogram tends to 0. The histogram will tend to a continuous smooth curve. Called the frequency curve. This curve doesn't have a formal name, so let me call it frequency curve. In the previous example, there are 30 data values in the data set, and the width of each class is 10. From 30 to 40 is 10. From 40 to 50 is 10. From 50 to 60 is 10. Now, assume the size of the data set becomes very, very large. Assume, say, there are 3,000 data values. Assume there are 3,000 data values. And the width of each class becomes very, very small. Assume the width of each class is about 0.1. Assume the width of each class is 0.1. Then the histogram looks like this. If the data set becomes if the size of the data set becomes very, very large, and the width of each class interval becomes very, very small, then histogram will look like this. Assume the width of each class becomes very, very small. That's how the histogram looks like. When the size of the data set becomes very, very large, and the width of each class interval becomes very, very small. That's how the histogram looks like. Here you can see that this histogram tends to a continuous smooth curve. This histogram tends to a continuous smooth curve. This histogram tends to a continuous smooth curve. You can see that the more data value, the smaller class interval. The more data value we have, and the smaller class interval we have here, the smooth the curve will be. The smaller class interval, the more data value, the smaller class interval, the smaller class width, the smooth the curve is. The smaller class width, the smooth the curve is. And this curve is called the frequency curve. It doesn't have a formal name, and let's call it frequency curve. So we can see that as the data size becomes very, very large, and the class width becomes very, very small, the histogram tends to a continuous smooth curve. That's called the frequency curve. Now, suppose there exists a real number c such that for all real number x, the relative rate of change the fall off in the frequency curve is proportional to the distance from c to x. Then we say the data value in the data sets. The data values in the data set. We say the data values in the data set are normally distributed. Then we say the data value in the data set are normally distributed. Suppose there's a real number c. Assume c is here in the center of the curve, such that for all real number x, assume x is somewhere here. Then we can see that as x move away from c, the curve falls off. The frequency curve falls off in both directions. As x move away from c, the frequency curve falls off. If the relative rate of the fall off in the frequency curve is proportional to the distance from c to x, then we say the data values in the data set are normally distributed. Now, how to express this relation here? The relative rate of the fall off in the frequency curve is proportional to the distance from c to x. How do we express this relationship here? Assume this frequency curve is f of x. Let's call this curve y equal to f of x. Assume this curve is y equal to f of x in the xy plane. How to express the relative rate of the fall off? How to express relative rate of fall off? We know that derivative of x represents the rate of change. F prime of x represents the rate of change. What's relative rate of change? What's relative rate of change? What's relative rate of change? If I take f prime of x divided by f of x, that's called the relative rate of change. That's called the relative rate of change. F prime of x is called the rate of change. F prime of x divided by f of x is called the relative rate of change. Negative rate of fall off means the derivative is negative. The rate of change is negative. Falling off means the rate of change is negative. What does proportional means? What does something is what does proportional means? What does the word proportional means? If we say A is proportional to B, what does it mean? If I say A is proportional to B, A is proportional to B, what does it mean? If we say A is proportional to B, that means A equal to some constant times B. If we say A is proportional to B, that means A equal to some constant times B. That's what proportional means. If we say A is proportional to B, that means A equal to K times some constant times B. A is proportional to B means A equal to some constant times B. What does distance? What does distance mean? Distance from C to A, what does it mean? Distance from C to A, it means what? Distance from C to A, from C to X, usually it means X minus C. Distance from C to X, usually it means X minus C. That's what it means. Now, how do we write this together? How do we write everything together? The relative rate of the fall off in the frequency curve is proportional to the distance from C to X. The relative rate of change is f prime of x over f of x. That's the relative rate of change. It's proportional to distance from C to A. A is proportional to B, that means A equal to K times B. So, the relative rate of change is proportional to distance from C to X. So, the relative rate of change is proportional to distance from C to X. That's what this expression says. And since the curve is falling off, the rate of change must be negative. So K must be less than 0. Since the curve is falling off, the rate of change must be negative. So this equation here, it represents that the relative rate of the fall off in the frequency curve the relative rate of the fall off in the frequency curve is proportional to the distance from C to X. It's proportional to the distance from C to X. So, if a data set is normally distributed, we always have this property. Then the relative rate of the fall off in the frequency curve is proportional to the distance from C to X. Now, when a delta value is randomly chosen from a normally distributed data set. Let the continuous random variable then a continuous random variable x represent the value of the total number. Then we say x has a normal distribution. But data value is randomly chosen from a normally distributed data set. Then a continuous random variable x represents the value of the total number. Then we say x has a normal distribution. Next, we try to find the PDF of x. Next, we try to find the PDF of x, the probability density function of x. We try to find the probability density function of x. Called f of x. Here, keep one idea in mind. Since we choose a data value randomly from a data set, that means for any data value in the data set, the higher frequency, the more chance it will be chosen. For any data value in the data set, the higher frequency, the more chance it will be chosen. That means the PDF of x will have the same property as this frequency curve. The PDF of x will have the same property as this frequency curve. Keep this idea in mind. Note, since a data value is randomly chosen from the data set, the higher frequency the higher chance it will be chosen. Then I can say that the PDF of x has the same property as the frequency curve. Same property as the frequency curve of the data set. For any data value in the set, the higher frequency, the more chance it will be chosen. So the PDF of x has the same property as the frequency curve of the data set. So the PDF of x also has a property that the relative rate of the fall off in the frequency curve is proportional to the distance from C to x. The PDF of x also has this property here. Since the PDF of x has the same property as the frequency curve of the data set, then we know that there exists a real number C such that for all real number x, the relative rate of the fall off in the PDF, the relative rate of the fall off in the PDF is proportional to the distance from C to x. So we have this equation here. So I have this equation here. F prime of x over f of x equal to k times s minus c, where k is a real number less than 0. K is negative. So f prime of x over f of x equal to k times x minus c, where k is less than 0. K is negative. Now, based on this equation, find f of x. Based on this equation, try to find f of x. From this equation here, I can first of all multiply both sides by f of x. I can first multiply both sides by f of x first. If I multiply both sides by f of x, I have f prime of x equal to k times x minus c times f of x. To make the expression look a little simpler, I can write f prime of x as dy over dx, assuming y is f of x. I can write f prime of x as dy over dx equal to k times x minus c. F of x is y. So I can write this equation in this form. Dy over dx equal to k times s minus c times y, where y is f of x. Then I can multiply both sides by dx, divide both sides by y, multiply both sides by dx. I have 1 over y dy equal to k times x minus c times dx. Divide both sides by y, then multiply both sides by dx. Divide both sides by y, and multiply both sides by dx. Next, I can take integral on both sides. If I take integral on the left side, I get ln of absolute value of y. On the right side, k is a constant. Take antiderivative here. I get k times s squared over 2 minus cx plus constant c. Let me use a different letter. We have c already. Let me use a different letter. Say d. Plus a constant d. D is a constant. Next, we try to get y by itself. How can we get y by itself? Apply e to both sides. If I apply e to both sides, what do we get? Apply e to both sides. If I apply e to both sides, on the left side, e cancels ln. I get absolute value of y by itself. On the right side, I get e to the power of k times x squared over 2 minus cx plus d. That's the left side, that's the right side. I apply e to both sides. Next, simplify the right side. For the right side here, I can pull out half, make it a little easier. Pull out half. If I pull out half, what do I get? I get e to the power of k over 2 times s squared minus 2cx plus d. If I pull out half, I get x squared minus 2cx plus d. Now, for this term here, to make it a little easier, I try to complete square. We know that a squared plus 2ab plus b squared equal to a plus b squared. A squared minus 2ab plus b squared is a minus b squared. What we have here is s squared minus 2cx. It looks like this form. What's missing is a perfect square in the back. We have s squared in the front. So what's missing in the back is c squared. So if I add c squared here, what do we get? E to the power of k over 2 s squared minus 2cx plus c squared. If I add c squared here, this is a perfect square. But we cannot add c squared for free. When we add it, we need to subtract at the same time to keep it in balance. So add c squared, subtract c squared at the same time. If I add c squared, the first three terms form a perfect square. E to the power of k over 2 times x minus c squared. But this minus c is not free. I have to multiply this back, multiply this out. Take k over 2 times negative c squared. I have negative k over 2 c squared plus d. There's one term left, so I multiply k over 2 to c squared. I get negative k over 2 c squared plus d. Next, let me copy everything over. Here I copy everything from the previous page. Let's continue from here. The right side can be rewritten as e to the power of k over 2 times x minus c squared times e to the power of negative k over 2 c squared plus d. In general, any number a to the power of m plus n. That's a to the power m times a to the power of n. Consider we have e to the power of this plus this. So I can separate it as e to the power of this times e to the power of this, using this property here. Then next, absolute value of y equal to this. That means y itself is plus or minus. Y itself could be either positive or negative of this. Let me write the second term in the front. The second term contains all constants. K is a constant, C is a constant, D is a constant. Let me bring the second term to the front. I get e to the power of negative k over 2 c squared plus d times e to the power of k over 2 x minus c squared. Let me call this, this is a constant. K is a constant, C is a constant, D is a constant, E is a constant. This is a constant. Let me call this constant A. Let me call this constant A. So y equal to A, y equal to A times e to the power of k over 2 times x minus c squared, where A is plus or minus e raised to negative k squared over 2 c squared plus d. Let me call this A. It looks much simpler. And then we know that y is f of x. Y is f of x. So that's the PDF. F of x equal to A times e to the power of k over 2 to the power of s minus c squared. That's the PDF of the normal distribution. That's the PDF of the normal distribution. But we need to find constant A, K, and C. A, K, and C, they're all constants. We must find these three constants. A, K, and C, they're all constants. We must find these three constants. How do we find a constant? How do we find a constant? Next, if I try to compute the expected value of x, what do we get? How do we compute expected value of x? Since x is a continuous random variable, we take integral from negative infinity to infinity, x times f of x dx. What's f of x? F of x is the PDF, which is a times e to the power of k over 2 times x minus c squared. So f of x is a times e to the power of k over 2 times x minus c squared dx. Then how do we solve this integral? We can try to use u substitution. We can try to use u substitution. If I let u be the exponent, k over 2 times x minus c squared, what's my du? My du will be k times x minus c dx. But here we only have x. We don't have k. We don't have x minus c. K is a constant. That's okay. But we don't have x. We are missing x minus c. What can we do? In order to make the integral easier, let's change our plan. Let's change our plan. Let me try to find e of x minus c first. So instead of finding e of x, let me try to find e of x minus c first. In order to make the integral easier, let me change my plan. Let's change our plan. Let's find e of x minus c first. How do we find e of x minus c? Since x is a continuous random variable, take integral from negative infinity to infinity. X minus c times f of x dx. F of x is a times e to the power of k over 2 times s minus c squared. A times e to the power of k over 2 x minus c squared dx. If I make u substitution, what do I get? I have 1 over k here. We have x minus c. We're missing a k, so I have 1 over k here times a. E to the power of u du. What should we put here for the limit? If I plug infinity for x, infinity minus a constant is infinity. Infinity squared is positive infinity. Here k is a negative number. K is a negative number. Negative number over 2 is negative. A negative number times infinity is infinity. If I plug in negative infinity again, negative infinity minus c is negative infinity. Negative infinity square is positive infinity, but k is negative. So negative number times infinity is negative infinity. When we have integral from negative infinity to infinity, we can't tell which infinity is larger, which is smaller. In general, infinity minus infinity is indeterminate form. We don't know which one is larger, which one is smaller. In general, when we have infinity minus infinity, that's called indeterminate form. We don't know which infinity is larger, it's not zero. Infinity minus infinity, usually answer is not zero. We don't know which infinity is larger. If they are the same, answer is zero, but usually they are not the same. So in this case, we must consider improper integrals. This is improper integral. Let me break this into two integrals. First integral from negative infinity to c. Second integral from c to infinity. X minus c, a times e to the power of k over 2, x minus c squared dx. Let me solve for the first integral first. Then solve the second one. For the first integral, make a substitution. If I plug in if I plug in c for x, c minus c is 0. 0 times everything is 0. Upper limit is 0. If I plug in negative infinity square is infinity. Infinity times the negative number is negative infinity. Then we have s minus c. We are missing a k, so I take 1 over k times this, times a, times e to the power of u, k over 2 times s minus c squared is u, du. Then a over k is a constant. 1 over k times a, that's a constant. So a over k is a constant, I can pull it outside. Take antiderivative for e to the power u. That stays the same. Evaluate from negative infinity to 0. What do we get here? If I plug in 0, e to the power of 0 is 1. I get a over k. If I plug in negative infinity, e raised to negative infinity is 0. So the first integral is a over k. Now let's do the second integral. If I make a substitution, if I plug infinity for x, infinity minus constant is infinity. Infinity squared is infinity. Since k is less than 0, negative number times infinity is negative. So I get negative infinity. Negative number times infinity is negative infinity. If I plug in c for x, c minus c is 0. 0 times k over 2 is 0. So same thing, we have s minus c, we are missing a k. So we get 1 over k times a times e to the power of u du. Then 1 over k times a, that's a constant, I can pull it outside. If I pull it out, I get a over k times integral times the integral of e to the power of u. If I take antiderivative for e to the power of u, I get e to the power of u. Then evaluate from 0 to negative infinity. If I plug in negative infinity, e raised to negative infinity is 0. If I plug in 0, e to the power of 0 is 1. So together I get a over k plus negative a over k, which is 0. That means expected value of x minus c is 0. Expected value of s minus c is 0. Expected value of s minus c can be rewritten as e of x minus e of c. And we know that expected value of a constant is a constant itself. S is a constant. Sorry, c is a constant. Expected value of c is c itself. Expected value of a constant is the constant itself. Then if I solve an equation for c equal to expected value of x, c equal to expected value of x. And we know that expected value of x is mu. expected value of x is mu. So c equal to mu. Here we found the first constant, c equal to mu. Here we found the first constant, c equal to mu. Mu is an expected value. It's also called a mean. Mu is the expected value. It's also called the mean. Now, if I run a PDF here, what do we get? F of x equal to a times e to the power of k over 2 times x minus c squared. We know that c is mu, so I write x minus mu squared. Next, we try to find k by using the variance. We try to find k by using the variance. How do we find variance of x? Variance of x is an expected value of x minus mu squared. Expected value of x minus mu squared. How do we find the expected value of x minus mu squared? Since x is a continuous random variable, take integral from negative infinity to infinity. S minus mu squared times f of x dx. Then f of x is a times e to the power of k over 2 times s minus mu squared. Let's plug in. Take integral from negative infinity to infinity. S minus mu squared. F of x is a times e to the power of k over 2 times s minus mu squared dx. Then how do we solve this integral? For this integral, we can try to use integration by part. For this integral, we try to use integration by parts. Let me rewrite the integral first. This integral can be rewritten as integral from negative infinity to infinity. A times s minus mu times another s minus mu times e to the power of k over 2 times s minus mu squared dx. Use integration by parts. Let u, this is u, be very careful, u and mu is different. U and mu is different. Let u equal to a times s minus mu. Let dv be s minus mu times e to the power of k over 2 times s minus mu squared dx. Then we take derivative for u, take antiderivative for dv. If I take derivative for u, what's my du here? A is a constant, stays the same. Derivative of x is 1. Derivative of mu is 0. Mu is a constant. Derivative of mu is 0. So I get a times dx. Derivative of x is 1. 1 times dx is 1 dx. Then take antiderivative for dv. If we take antiderivative for dv, what do we get? Let me solve it here. Antiderivative of dv, s minus mu times e to the power of k over 2 s minus mu squared dx. How do we solve this integral? Here we can try to use u substitution. Let t equal to k over 2. Let t equal to the exponent. K over 2 times s minus mu squared. What's dt here? If I take derivative for t, what do we get? What's dt here? Dt is k times s minus mu dx. We have s minus mu. We are missing a k. So I can divide both sides by k. 1 over k dt equal to s minus mu dx. So we have e to the power of t times s minus mu times dx is 1 over k dt times 1 over k dt. 1 over k is constant, so when we take antiderivative, it stays the same. For e to the power of t, If I take antiderivative, it also stays the same. Plus c. Then replace t. Replace t with k over 2 times s minus mu squared. Plus c. So that's the antiderivative of this expression. So if I take antiderivative for dv, I get 1 over k times e to the power of k over 2 times s minus mu squared. V is 1 over k times e to the power of k over 2 times s minus mu squared. Next, use the formula. We have u times v minus v times du. U times v. If I take u times v, I have a over k times s minus mu times e to the power of k over 2 times x minus mu squared. Evaluate from negative infinity to infinity. Minus integral of v du. V times du. If I take v times du, we have a over k times e to the power of k over 2 times s minus mu squared dx. Let me deal with this one first, then I'll solve the other one. Let me solve this one first. If I plug infinity, what do we get? If I plug in upper limit infinity, what do we get here? If I plug infinity, I plug infinity for x. Infinity minus mu is infinity. If I plug infinity here for x, infinity minus mu is infinity. Infinity squared is infinity. But k is negative. K is less than 0. Negative number times infinity is negative infinity. E raised to negative infinity is 0. We get infinity times 0. That's indeterminate form. That's indeterminate form. We must take limit by using L'Hopital's rule. So let me rewrite this over. Take limit as t approaches to infinity, and I'm plugging t for each x. Take limit as t approaches to infinity, then I'm plugging t for each x. I get a over k times t minus mu times e to the power of k over 2 t minus mu squared. This limit can be rewritten as a over k times t minus mu. I bring e to the bottom. E to the power of negative k over 2 t minus mu squared. If I plug infinity, I get infinity on the top. If I plug infinity on the bottom, infinity minus mu is infinity, infinity squared is infinity. And since k is negative, double negative is positive. Positive number times infinity is positive infinity. E raised to infinity is infinity. Here we get infinity over infinity, we can use L'Hopital's rule. If we use L'Hopital's rule, what do we get? If I take derivative from the numerator, I get 1. If I take derivative from the denominator, I get e raised to negative k over 2 times t minus mu squared times, use chain rule, times negative k times t minus mu. If I plug in infinity one more time, infinity minus mu is infinity, infinity squared is infinity. Since k is negative, double negative become positive. Positive number times infinity is positive infinity. E raised to positive infinity is infinity. If I plug infinity here, infinity minus mu is infinity. K is negative, double negative become positive. Positive number times infinity is infinity. So on the bottom, infinity times infinity is infinity. 1 over infinity is 0. A over k times infinity is 0. So when I plug in infinity, this limit is 0. When I plug in infinity, this limit is 0. If I plug in negative infinity, what do we get? if we plug in negative infinity minus mu is negative infinity. If I plug in negative infinity, I get negative infinity minus mu, which is negative infinity. When I square it, becomes positive infinity, but k is negative. Negative number times infinity is negative infinity. E raised to negative infinity is 0. We get negative infinity times 0, which is also indeterminate form. So we must take a limit. So the limit is very similar. Take limit as t approach to negative infinity. A over k times t minus mu e to the power of k over 2 t minus mu square. First of all, put this in division form. Limit k approach to negative infinity a over k times t minus mu over e to the power of negative k over 2 t minus mu square. If I plug in negative infinity, the top is negative infinity. The bottom, negative infinity minus mu is negative infinity. When I square it, becomes positive infinity. And k is negative. Double negative becomes positive. Positive number times infinity is infinity. E raised to infinity is infinity. We're still in the form of infinity over infinity. The sign doesn't matter. So use L'Hopital's rule again. Use L'Hopital's rule here. T approach to negative infinity. Use L'Hopital's rule. I get a over k. If I take derivative from the numerator, I get 1. From the denominator, I get e to the power of negative k over 2 t minus mu square times negative k times t minus mu. If I plug in negative infinity minus mu is negative infinity. When we square it, it's positive infinity. And k is negative, double negative is positive. Positive number times infinity is infinity. E raised to infinity is infinity. Negative infinity minus mu is negative infinity. K is negative, double negative becomes positive. Positive number times negative infinity is negative infinity. 1 over infinity. 1 over negative infinity is 0. So we get a over k times 0, which is 0. So if I take limit by plugging negative infinity, I also get 0. So the first part becomes 0. Now the second part here. Second part, a over k times e to the power of k over 2 s minus mu square. It looks very similar as the PDF, except this k on the bottom. If I pull out this k on the bottom, what do we get? I get 1 over k times the integral from negative infinity to infinity a times e to the power of k over 2 s minus mu square dx. Since this is PDF, this is a PDF of x. Since this is a PDF of x, the total area under the curve must be 1. The total area under the PDF must be 1. The total area under this curve must be 1. So this integral is 1. So we get 0 minus 1 over k times 1. This is a PDF. The integral from net infinity to infinity of a PDF must be 1. The total area under the PDF must be 1. So we have variance of x equal to negative 1 over k. Variance of x equal to negative 1 over k. We know that variance of x is sigma square. Variance of x is sigma square. They equal to negative 1 over k. If I solve this equation for k, k equal to 1 over negative 1 over sigma square. If I solve this equation for k equal to negative 1 over sigma square. Now let me run a PDF and put it here. F of x is a times e to the power of k over 2 times s minus mu square, where k, we just found it, k is negative 1 over sigma square. If I plug in k, what do we get? F of x equal to a times e to the power of 1 over 2 times k. K is negative 1 over sigma square times s minus mu square. So f of x can be rewrite as a times e to the power of negative s minus mu square over 2 sigma square. Multiply s minus mu square to the numerator. Multiply 2 times sigma square on the denominator. Pull out negative sign. That's the PDF. Now what's missing here is a. Next, we have to find a. How do we find a? We know that since f of x is a PDF, the total area under the curve must be 1. If I take integral from negative infinity to infinity, f of x dx, this integral must eventually be 1. So take integral, and I can solve for a. Take integral, set it equal to 1, and then solve for a. Plug in f of x, take integral, then solve an equation for a. How do we take integral here? I first of all plug in f of x. F of x is a times e to the power of negative s minus mu square over 2 sigma square dx. This can be rewrite as integral from negative infinity to infinity a times e to the power of negative s minus mu over radical 2 times sigma square dx. If I make u substitution here, what can we get? What do we get? If I make u substitution here, if I let t equal to x minus mu over radical 2 times sigma, what do we get? My dt is 1 over radical 2 times sigma dx. So radical 2 times sigma dt will be dx. If I plug in infinity minus mu over 2 times sigma. Sigma is always positive. Infinity minus mu is positive, is infinity. Radical 2 times sigma. Sigma is positive. So infinity over a positive number is positive infinity. If I plug in negative infinity minus mu is negative infinity. Sigma is positive. Radical 2 times sigma is also positive. Negative infinity over a positive number is negative infinity. A stays the same. This part become t. S minus mu over radical 2 sigma become t. dx is radical 2 times sigma dt. Then a is a constant, radical 2 is a constant, sigma is constant, I can put it outside. I have radical 2 times a sigma. Radical 2 sigma times a. Integral negative infinity to infinity e to the power of negative t squared dt. How do we solve this integral? In order to solve this integral, we need to use multivariable calculus. So it's from negative infinity to infinity e raised to negative t squared dt. Let me set this equal to I. Then I squared equal to I times I. This part requires multivariable calculus. I squared equal to I times I. For the first I can write integral from negative infinity to infinity e raised to negative x squared dx. Second integral, second I, take integral from negative infinity to infinity, e raised to negative y squared dy. This integral and this integral, they are exactly the same. I change t to x, they are exactly the same. The value is exactly the same. I change t to y, their value is exactly the same. Then I can combine these two integrals together. Integral x from negative infinity to infinity, y from negative infinity to infinity. Since the limits are constants, then I can multiply these two functions together. E to the negative x squared minus y squared dy dx. Then if we use polar coordinate, x squared plus y squared equal to r squared, dy dx equal to dA, and in polar coordinates dA equal to r dr d theta. So this part we have e to the power of negative r squared, dy dx is r dr d theta. If x is from negative infinity to infinity, y is from negative infinity to infinity, that means we take integral over in the entire xy plane. If s is from negative infinity to infinity, y is from negative infinity to infinity, that means we take integral over the entire xy plane. So theta is from 0 to 2 pi. For both cycles, theta is from 0 to 2 pi. R, consider r as a radius. R is from 0, start from 0, getting larger, 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 larger. So r is from 0 to infinity. Then take the inner integral first. Keep the outer integral the same. Take the inner integral first. For the inner integral, make u substitution. The u equal to negative r squared. Then du will be negative 2r dr. We have an r here, so I divide both sides by negative 2. Half of du is r dr. So we get e to the power of u times negative half du. And the limit here, if I plug in infinity, infinity squared is infinity. Negative, and add negative sign in the front, I get negative infinity here. U is negative infinity. On the bottom, if I plug in 0, negative 0 squared is 0. D theta. Then take antiderivative. Antiderivative of e to the power of u stays the same. Negative half is a constant. It also stays the same. So I get negative half e to the power of u. Evaluate u from 0 to negative infinity. D theta. Theta is from 0 to 2 pi. If I plug in negative infinity, e raised to negative infinity is 0. If I plug in 0, e to the power 0 is 1. Then together, theta from 0 to 2 pi. Double negative is positive, half of d theta. Then take antiderivative, I get half of theta. Evaluate theta from 0 to 2 pi. If I plug in 2 pi, I get half of 2 pi. If I plug in 0, I get 0. So the answer is pi. So I squared equal to pi. I square equal to pi. I square equal to pi. That means I itself equal to square root of pi. So this integral equal to square root of pi. This integral equal to square root of pi. This integral requires multivariable calculus. If you don't know multivariable calculus, you can memorize the answer. Skip the detail. Memorize the answer. This integral is square root of pi. Then multiply. We have radical 2 pi times sigma times a. And we know that since f of x is a PDF, integral from negative infinity to infinity must be 1. Total area under a PDF must be 1. So I set radical 2 pi times sigma a equal to 1. If I solve this equation for a is 1 over radical 2 pi. Over radical 2 pi times sigma. Sigma is outside square root. Be very careful. Sigma is outside square root. 1 over radical 2 pi times sigma. Sigma is outside square root. Here, if I plug in a into the PDF, I have f of x equal to 1 over radical 2 pi times sigma times e to the power of negative x minus mu square over 2 sigma square. That's the PDF of x, where x has a normal distribution. That's the PDF of x, where x has a normal distribution. Next, let me rewrite everything over. For normal distribution, when a data value is randomly chosen from a normally distributed data set, then the continuous random variable x represent the value of the chosen data value, the value of the chosen number. The value of the chosen number. The x represents the value of the chosen number. Then we say x has a normal distribution. And the PDF of x the PDF of x is f of x equal to 1 over square root of 2 pi times sigma times e to the power of negative x minus mu square over 2 sigma square, where s can be any real number. X is from negative infinity to infinity. So the support of x is the interval from negative infinity to infinity. In the formula, mu represents the mean expected value, which is the mean. Mu represents the mean. Mu is the expected value, which represents the mean. Sigma square is the variance. Sigma square is the variance. Sigma itself is the standard deviation. Sigma itself is the standard deviation. The notation for normal distribution is x has a normal distribution For normal distribution, there are two parameters, mu and sigma. Usually we write sigma square to make it easier. To avoid square roots, we write sigma square. So for normal distribution, there are two parameters, mu and sigma square. Mu is the mean. Sigma square is the variance. Sigma itself is the standard deviation. That's the notation for normal distribution. Or sometimes we can simply write x is n of mu and sigma square. That's a shortcut. Instead of writing normal, write n. N stands for normal. That's a shortcut for normal distribution. Next, let's look at an example. Let x be a random variable with x has normal distribution with mu equal to 100, sigma square equal to 64. Find each of the following probabilities. Part A, find the probability that s is between 96 and 110. Part B, find the probability that s is greater than or equal to 80. So let's first of all set out the problem first. Here x has a normal distribution with mu equal to 100 and sigma square equal to 64. Mu equal to 100, sigma square equal to 64. Then take square root, we can find sigma is a. Next, let's write down PDF of x. The probability density function of x. The formula is 1 over square root of 2 pi times sigma. Sigma is outside the square root. Times e to the power of negative x minus mu square over sigma square over 2 sigma square. For x between negative infinity and infinity. For all real number x, from negative infinity to infinity. Then we can plug in mu and sigma. If we plug in mu and sigma, what do we get here? Sigma is a. If I plug in a here, I have 1 over a square root of 2 pi. Sigma is a. So on the bottom, if I plug in a here, I get 2 times a squared, which is 128. On the numerator, mu is 100, So you get x minus 100 squared. So the formula is e to the power of negative x minus 100 squared over 128. Then, not on the support. What's the support of x? For normal distribution, support of x is always from all real numbers from net infinity to infinity. For normal distribution, support of x is always all real numbers from net infinity to infinity. Now, based on this, answer the question. Part A. What's the probability that x is between 96 and 110? Since x is a continuous random variable, we take integral. Take integral from 96 to 110. 1 over a square root of 2 pi times e to the power of s minus 100 squared over 128 dx. Solving this integral manually is almost impossible. Here I use my calculator. I get 0.5858. Here I use my calculator. Round to 4 decimal places, I get 0.5858. Part B. What's the probability that s is greater than or equal to 80? Since x is a continuous random variable, we take integral from 80 to infinity. Since s is a continuous random variable, take integral from 80 to infinity. 1 over a square root of 2 pi e to the power of negative x minus 100 squared over 128 dx. Then again, use my calculator. I get 0.9938. Round to 4 decimal places, I get 0.9938. Is there any simpler way? Even though we can use calculator, but typing in this formula may still be too long. Is there a simpler way to find the probabilities? The answer is yes. Next, let me introduce the standard normal distribution. Let x be the random variable. With x has a normal distribution with mu and sigma square. When mu is 0 and sigma square is 1, we say x with mu equal to 0, sigma square equal to 1 has the standard normal distribution. With PDF, with the probability density function f of x. In general, the probability function for normal distribution is 1 over square root of 2 pi times sigma times e raised to negative x minus mu squared over 2 sigma squared, where x is between negative infinity to infinity. That's the probability density function for normal distribution in general. But here we have mu equal to 0, sigma squared equal to 1, which means sigma is also 1. So I plug in 1 for sigma, plug in 0 for mu. if I plug in 1 for sigma, this PDF can be rewritten as 1 over radical 2 pi. If I plug in 1 for sigma square, 0 for mu, I have e to the power of negative x squared over 2. Where x is between negative infinity to infinity. S can be any real number from negative infinity to infinity. That's the standard normal distribution. That's a PDF of the standard normal distribution. That's much simpler than the general probability density function for normal distribution. Now, let's look at a theorem. Let x be the random variable with x has normal distribution with mu and sigma squared. Let z be the random variable with z equal to x minus mu over sigma. Then z has the standard normal distribution, which means z has a normal distribution with mu equal to 0 and sigma squared equal to 1. Let's prove it. How do we prove z has a standard normal distribution? If we try to prove z has a standard normal distribution, we must show that its PDF looks exactly like this. We need to show that its PDF f of z equal to 1 over radical 2 pi times e to the power of negative z squared over 2. If we try to show z has a standard normal distribution, we must show that its PDF looks exactly the same as this. Now, how do we find its PDF? Let g of z be the PDF of z. Finding the PDF directly is very hard. Finding the PDF of z directly is very hard. Let's find CDF first. And let g of z be the CDF of z. Then once we know the CDF, by taking derivative, I can find the PDF. Once we know the CDF, by taking derivative, we can find the CDF. We can find the PDF. So find the CDF first. Once we know the CDF, by taking derivative, we can find the PDF. How do we find CDF of z? What's CDF of z? In general, the CDF f of x is the probability that x less or equal to x. In general, the CDF f of x is the probability that x less or equal to x. So similarly, the CDF g of z is the probability that z less or equal to z. And we know that here z is x minus mu over sigma. So we have x minus mu over sigma less or equal to z. Then we try to look at s by itself. I can first of all multiply both sides by sigma. If I multiply both sides by sigma, I get x minus mu less or equal to z times sigma. Next, I can add mu to both sides. If I add mu to both sides, I have x less or equal to mu plus z sigma. What's the probability that x is less or equal to mu plus z sigma? Since x is the normal distribution with mu and sigma squared, x is a continuous random variable. So for probability that x is less than or equal to mu plus z sigma, I take integral from negative infinity to mu plus z sigma times the PDF, integral of the PDF f of x dx. X is the normal distribution with mu and sigma squared. What's its PDF? Its PDF is, the PDF of x is 1 over radical 2 pi times sigma. X is not a standard PDF, it's not a standard normal distribution. we must use the general PDF of normal distribution. 1 over radical 2 pi times sigma times e to the power of x minus mu square over 2 times sigma square dx. That's the general PDF for normal distribution x. So that's g of z. This is the CDF g of z. Then once we know the CDF, by taking derivative, I can find the PDF. This is CDF g of z. This expression is a CDF g of z. Using the CDF, if I try to find the PDF, I take derivative. If I take derivative on both sides with respect to z, what do we get here? Take derivative on both sides with respect to z. On the left side, the derivative of the CDF is the PDF g of z. On the left side, the derivative of the CDF is the PDF g of z. On the right side, how do we take derivative here? This is the derivative of an integral. When we're taking derivative for integral, we're using the fundamental theorem of calculus. Here in the integral, the variable is x. If the lower limit is a constant, I plug in the upper limit for x. The variable here is x. I plug in upper limit for x. Then take derivative from the upper limit by chain rule. I plug in upper limit for x. Then take derivative from the upper limit with respect to z because of chain rule. So derivative cancel integral. I get 1 over radical 2 pi. 1 over radical 2 pi times sigma times e to the power of negative. I plug in upper limit for x, so I get mu plus z sigma minus mu square over 2 sigma square. Plug in upper limit for x, then by chain rule times the derivative of an upper limit with respect to z. If I take derivative with respect to z, mu is a constant, so I get sigma by itself. We got sigma itself. Sigma is the derivative of an upper limit. Since mu and sigma they are both constants, I take derivative with respect to z, I get sigma. Then if I simplify, this sigma cancel this sigma here. I get 1 over radical 2 pi. Mu minus mu get cancel. We get z sigma square. We get z sigma square in the parentheses. Z sigma square over 2 sigma square. This sigma can cancel here. Now, if I multiply, I get z squared times sigma square. If I multiply, I get z squared times sigma square. Sigma square get cancelled. So I have g of x, g of z is 1 over radical 2 pi times e to the power of negative z squared over 2. If I distribute square, I get z squared times sigma square. Cancel sigma square, I get z squared on the top, 2 on the bottom. This is the PDF of G. This is the PDF of Z. And it looks exactly the same as this f of x here. 1 over radical 2 pi times e raised to negative x squared over 2. Since the PDF of Z looks exactly the same as a standard normal distribution, then we can say Z has a standard normal distribution. Let's complete the proof. Since the PDF of Z looks exactly the same as a standard normal distribution, so we can say Z has a normal distribution. Z has a standard normal distribution. Let's complete the proof. Note, according to the previous theorem, we know that the formula Z equal to x minus mu over sigma can convert any normal distribution x with mu and sigma square to the standard normal distribution. With Z has mu equal to 0 and sigma square equal to 1. And also, the PDF, the probability density function of Z, is always f of Z equal to 1 over radical 2 pi times e to the power of negative z squared over 2. Where z can be any real numbers from negative infinity to infinity. There's no difference calling the PDF f or g. There's no difference calling the function f or g. In general, we use function f to represent the PDF. Now, let's redo example 1 using the standard normal distribution. Using the standard normal distribution. In example 1, x has a normal distribution with mu equal to 100 and sigma squared equal to 64. So here, mu equal to 100, sigma squared equal to 64, which means sigma equal to A. Part A, we're looking for probability that x is between 96 and 100. X between 96 and 110. In order to use the standard normal distribution, we must convert x to z. So the formula is x minus mu over sigma. 96 minus mu over sigma. And the other one take 110 minus mu over sigma. Then we have z is between negative 0.5 and 1.25. Since z is the standard normal distribution, we take integral from negative 0.5 to positive 1.25 f of z dz, and we know that this is f of z. We have 1 over radical 2 pi times e raised to negative z squared over 2 dz. Then I use my calculator. I get 0.5858. Part B. Find the probability that x is greater than or equal to 80. Same thing, convert x to z. The formula is z equal to s minus mu over sigma. So take at minus mu over sigma. Sigma is a. At minus 100 is negative 20. Negative 20 divided by a is negative 2.5. Then since z is the standard normal distribution, we take integral from negative 2.5 to infinity. 1 over radical 2 pi times e raised to negative z squared over 2 dz. Then I use my calculator. Round to 4 decimal places, I get 0.9938. Using the standard normal distribution, the PDF is a little simpler. But still, there's too much work. Is there another better way to do the problem? The answer is yes. Next, I'll show you how to use the standard normal CDF to find probabilities. The standard normal CDF. Phi of z. Phi is a Greek letter. This is a Greek letter phi. Phi of z stands for the standard normal CDF. Let phi of z be the CDF of the standard normal distribution. Z is the standard normal distribution with mu equal to 0, sigma squared equal to 1. Then probability that z less or equal to z is phi of z, and probability that z strictly less than z. Theoretically, that's phi of z taking limit from left side. That's a CDF of z, CDF phi of z taking limit from left side. But z is the standard normal distribution, which is a continuous random variable. Since z is a continuous random variable, it must have continuous CDF. So z has continuous CDF. Since z has continuous CDF, the limit from left side and right side must be the same everywhere. For all z's, limit from left side or right side must be the same everywhere. So phi of z taking limit from left side must be the same as phi of z. So probability that z less or equal to z and probability that z strictly less than z, they both equal to phi of z. And for the standard normal CDF phi of z, there's a table. We can find the value of phi of z from this table. This table is called a standard normal CDF phi of z. We can find the value of phi of z from this table. Now let's do example 1 using the standard normal CDF phi of z. Redo example 1 using the standard normal CDF. In example 1, we know that x has a normal distribution with mu equal to 100, sigma squared equal to 64. So sigma must be A. A, we're looking for probability that S is between 96 and 110. So first step, we convert X to Z. Convert X to the standard normal distribution. Convert X to Z. The formula is 96 minus mu over sigma squared over sigma. Sigma is A. And then take 110 minus mu over sigma. Then here we found that z is between negative 0.5 and 1.25. If we try to use CDF to find the probabilities, we must rerun the probability in the form of z less or equal to some number. We must rerun the probability in the form of z less or equal to some number, or z strictly less than some number. They both equal to phi of z. They both equal to phi of z. So try to write probability in the form of z less or equal to some number, or z less than some number. That can be written as, if we consider everything from negative 0.5 and 1.25, consider this line segment represent z less or equal to 1.25. 1.25 is here. We try to find a line segment z between negative 0.5 and 1.25. Assume that's negative 0.5. This line segment here is z between negative 0.5 and 1.25. Then, in order to get this line segment, I take the total line segment, take away this little piece, this tail here. Since I try to keep 0.5 here, negative 0.5 here, I take away everything that's below negative 0.5. I take away everything that's below negative 1.5. So, for this line segment, I take the total line segment, z less or equal to 1.25, take away the line segment, z less than 0.5. So, taking the total line segment, probability that z less or equal to 1.25, take away probability that z is less than negative 0.5. Taking the total line segment, take away the tail. What's left is this line segment from negative 0.5 to positive 1.25. Then here, probability that z is less or equal to 1.25, that's phi of 1.25. Probability that z is less than negative 0.5 is phi of negative 0.5. Then subtract. Find the value and subtract. How do we find the value phi of 1.25? How do we find the value phi of 1.25? So for phi of 1.25, consider the first two digits 1.2 and the last digit 5. Consider the first two digits 1.2 and the last digit 5. Let's find 1.2 first. Z is from negative 3.9, go all the way down to positive 3.9. So we first of all find 1.2. 1.2 is here. 1.2 is here. Last digit is 5. So we find 0.05 in the first row. 1.25. Intersection is here. It's about 0.89435. 0.89435. That's phi of 1.25. Phi of 1.25 is here. 1.2 and 5 intersection is here. 0.89435. 0.89435. That's phi of 1.25. Now the other one, phi of negative 0.5. So round it to two decimal places. Round it to two decimal places. negative 0.5 can be rewritten as negative 0.50. Negative 0.5 can be rewritten as negative 0.50. The first two digits is negative 0.5. The last digit is 0. So let's find negative 0.5 first. Negative 0.5 is here. Negative 0.5 is here. Last digit is 0. Negative 0.5 is here. Last digit is 0.0. The intersection is here. 0.30854. 0.30854. Negative 0.5. And the last digit is 0.0. Last digit is 0. Intersection is here. 0.30854. So phi of negative 0.5 is 0.30854. If we subtract, I get 0.185. I got 0.58581. I got 0.58581. If I round to 4 decimal places, it should be 0.5858. If I round to 4 decimal places, it should be 0.5858. That's exactly the same as what we have here. Part B. Find the probability that x is greater than or equal to 80. First of all, we need to convert x to the standard normal distribution. The formula is x minus mu over sigma. So here we take 80 minus mu is 100, over sigma is a. Then 80 minus 100 is negative 20. Negative 20 divided by a is negative 2.5. Since we are finding probability using CDF, we must derive probability in the form of g less or equal to some number, or g less than some number. Here we have g greater than or equal to some number, so we can use the complement. If I use the complement, I have 1 minus probability that g is strictly less than negative 2.5. Since g has continuous CDF, I can write it as 1 minus phi of 2.5, negative 2.5. 1 minus phi of negative 2.5. Probability that g less than some constant is phi of g. Probability that g less than g is phi of g. So probability that g less than negative 2.5 is phi of negative 2.5. Now we need to find phi of negative 2.5 in the table. Negative 2.5. Rounded to 2 decimal places, we have phi of negative 2.50. The first 2 digits is negative 2.5. Last digit is 0. Negative 2.5 is here. Negative 2.5 is here. Negative 2.5. And last digit is 0. Last digit is 0. Negative 2.5, 0. Here is negative 0.00621. The intersection negative 2.5, 0 is 0.00621. I get 1 minus 0.00621. That's phi of negative 2.5. If I subtract 1 minus 0.00621, that's 0.99379. If I round the answer to 4 decimal places, that's about 0.9938. If I round to 4 decimal places, I get 0.9938. That's exactly the same as what we have here. So here you can see that for normal distributions, finding probability using the table of the standard normal CDF is much easier than solving integrals. Next, let's practice more. Example 2. Let G be the standard normal distribution with mu equal to 0, sigma squared equal to 1, Find each of the following probabilities. Part A. What's the probability that z is less than 1.41? Since z is the standard normal distribution, and it's in the form of z less or equal to some z, or z less than z, it's in this form. They both equal to phi of z. They both equal to phi of z. So, probability that z is less than 1.41 is phi of 1.41. Use the table 1.41. 1.4 is here, 1.41 is here. I got 0.92073. 1.41, 0.92073. 0.92073. Usually round to 4 decimal places. It's 0.9207. Part B. Find the probability that z is less or equal to negative 2.33. Since function phi is the CDF, so probability that z less or equal to negative 2.33 is phi of negative 2.33. That's phi of negative 2.33. In the table, let's find negative 2.3 first. Negative 2.3 is here. And the last digit is 3. Negative 2.33 is here. 0.00990. 0.00990. 0.00990. If we round to 4 decimal places, that's 0.0099. Next example. Probability that z is greater than or equal to 2.04. Probability that z is greater or equal to 2.04. Since we are finding probability using the CDF, we must find the probability in the form of z less or equal to some number or z less than some number. Since here we have z greater or equal to 2.04, we can use the complement. It can be rewritten as 1 minus probability that z is less than 2.04. And probability that z is less than 2.04 is phi of 2.04. It's in this form. So that's phi of 2.04. Probability that z less than 2.04 is phi of 2.04. And for 2.04, we can find it in the table. 2.0 is here. Last digit is 4. So 2.04 is 0.97932. 0.97932. 0.97932. 1 minus 0.97932 is 0.02068. If we round to 4 decimal places, that's 0.0207. Part D. What's the probability that z is greater than negative 0.86? Since we are finding probability using the CDF, I try to write probability in this form. I try to put it in the form of z less or equal to some constant, or z less than some constant. Here we have probability that z greater than some number, so I can use the complement. Probability that z is greater than negative 0.86, its complement is probability that z is less than or equal to negative 0.86. It's in this form. Probability that z is less or equal to some number. That's phi of this number here. So that's phi of negative 0.86. Phi of negative 0.86. Negative 0.86. Let's find negative 0.8 first. Negative 0.8 is here. Last digit is 6. It's in the fourth column. 1, 2, 3, 4. It's in the fourth column. 0.86 is here. 0.19489. 0.19489. 0.19489. Then 1 minus 0.19489 is 0.80511. If I round to 4 decimal places, it will be 0.8051. Part E. Find the probability that z is between negative 1.39 and 1.06. Since we are finding probabilities using the CTF, we try to run the probabilities in the form of probability that z is less or equal to some number, or probability that z is less than some number. What can we write here? Here we have z between these two numbers. I can first of all draw a longer line segment from negative infinity to 1.06. That's the line segment. Z is less or equal to 1.06. Now, we try to have a line segment here for z is between negative 1.39 and 1.06. Assume negative 1.39 is here. We are looking for the line segment from negative 1.39 to 1.06. Z is between negative 1.39 and 1.06, including 1.06, not including 1.39. So I try to remove a tail from this entire line segment. From the tail here, we have z less or equal to 1.39. Because I don't want to include negative 1.39 here, so I need to remove the point negative 1.39. So for this line segment, I can find a probability for all z less or equal to 1.06 first. Then take away the tail. The tail is probability that z less or equal to negative 1.39. So as a shortcut I can memorize, first of all use probability that z is less or equal to the larger number, minus probability that z is less than or equal to the smaller number. For the larger number, whatever the size, whatever the symbol is, keep it the same. For the larger number, whatever the symbol is, keep it the same. For the smaller number, if there's no equal sign under inequality, we add it here. If there's no equal sign under inequality, we add it here. But if there is an equal sign under inequality, we remove it. It's the opposite. If there's no equal sign under inequality, we add it here. But if there is equal sign under inequality, we remove it. So if there's no equal sign under inequality, we add it here. But if there is equal sign under inequality, we remove it. It's always the opposite. For the larger number, equal sign stays the same. For the smaller number, when we subtract, if there's no equal sign, add equal sign under inequality. Then that's in the form of z less or equal to some number. I have phi of 1.06. That's in the form of z less or equal to negative 1.39. I have phi of negative 1.39. Then find phi of 1.06 and phi of 1.39 in the table. Phi of 1.06. 1.0 is here. 6 is here. I get 0.56356. 0.56356 minus negative 1.39. Negative 1.3 is here. And 0.09 is here. That's negative 1.39. I have negative 0. I have 0.08226. 0.08226. If I subtract, what do I get here? I have 0.4813. 6 minus 6 is 0. I get 0.4813. F. Find the probability that z is between 1.47 and 2.84. So I first of all take probability that z is less than 2.84 minus probability that for the larger number, inequality stays the same. It's less than 2.84 stays the same. Z less than 2.84. For a smaller number, if there's equal sign below inequality, remove it. Minus probability that z is less than 1.47. So for larger number, inequality sign stays the same. For a smaller number, if there's equal sign under inequality, remove it. If there's no equal sign under inequality, add it. It's an opposite. So rewrite the probability in the form of probability that z less or equal to some constant, and probability that z is less or equal to some constant first. Then that's phi of 2.84 minus phi of 1.47. Since we are finding probability using the CDF, we must always run the probability in the form of z less or equal to some constant or z less than some number. Always put it in this form first. Then use the CDF, the phi, function phi. Then for phi of 2.84, use a table. 2.84 is 0.99774. 0.99774. For phi of 1.47, 1.4 is here. 7 is here. 1.47, I have 0.92922. 0.92922. Then I use my calculator. I get 0.06852. If I round the answer to 4 decimal places, I get 0.0685. Next example, let x be the normal distribution with mu equal to 60 and sigma squared equal to 4. Find each of the following probabilities. Part A. Find the probability that x is less or equal to 58. Since x is not a standard normal distribution, we must convert x to the standard normal distribution first. The formula is z equal to x minus mu over sigma. And here, mu is 60 in x. Mu is 60. Sigma squared is 4. That means sigma is 2. So convert x to z first. Convert x to the standard normal distribution. So the formula is x minus mu over sigma. Take 58 minus mu over sigma. Sigma is 2. That's probability that z is less or equal to -1. Then, since this probability is in the form of probability that z less or equal to some number, that's phi of the number. And probability that z less or equal to some number is also phi of the number. Since this probability is in the form of z less or equal to -1, I can use the first formula. That's phi of -1. -1, if I round to 2 decimal places, is -1.00. For -1, if I round to 2 decimal places, it's -1.00. -1 is here. 0.0 is here. Be very careful. For negative number, 0 is in the last column. -1.00. I get 0.15866. I get 0.15866. If I round to 4 decimal places, if I round the answer to 4 decimal places, it will be 0.1587. Part B. What's the probability that x is greater than or equal to 63? First of all, let's convert x to z. Convert x to the standard normal distribution. The formula is x minus mu over sigma. Mu is 60. Sigma is 2. So that's probability that z is greater than 1.5. 3 divided by 2 is 1.5. Since we are finding probabilities using the CDF, I try to put a probability in the form of probability that z less or equal to some number, or probability that z less than some number. Since we have probability that z greater than some number, we try to use the complement. The complement is 1 minus probability that z is less or equal to 1.5. Probability that z is less or equal to 1.5, that's phi of 1.5. That's phi of 1.5. Then use the table. Phi of 1.5. 1.5 is here, 0 is here. 1.50, I get 0.93319. I get 0.93319. Then subtract, I get 0.0668. If I round to 4 decimal places, it will be 0.0668. Part C. Find the probability that S is between 55 and 59. Find the probability that S is between 55 and 59. First of all, let's convert X to the standard normal distribution. Convert S to Z first. The conversion is X minus mu over sigma. 55 minus 60 over sigma. Sigma is 2. And here we use 59 minus sigma minus mu over sigma. Sigma is 2. That's probability that Z is between negative 2.5 and negative 0.5. Then we try to run a probability in the form of probability Z less or equal to Z, or probability that Z less than some number. So here I can write it as probability that Z is less than 0.5, negative 0.5. Z is less than a larger number. This inequality sign stays the same. Minus probability that Z is less or equal to negative 2.5. For this inequality sign, change it. If there is no equal sign under inequality, add it here. If there is equal sign under inequality, remove it. But if there is no equal sign under inequality, add it here. Then I put a probability in this form. I can write it in terms of phi, function phi. That's phi of negative 0.5 minus phi of negative 2.5. Phi of negative 0.5 and phi of negative 2.5. Negative 0.5 is here. Negative 0.5. Last digit is 0. Negative 0.50 is 0.30854. 0.30854. Minus phi of negative 2.5. Negative 2.5 is here. Last digit is 0. We have 0.00621. 0.00621. Subtract, we get 0.30233. If I round the answer to 4 decimal places, it will be 0.3023. That's part C. Part D. Find the probability that S is between 57 and 61. Find the probability that S is between 57 and 61. So, first step, convert X to the standard normal distribution. Convert S to Z. the formula is x minus mu over sigma x minus mu over sigma. So here z is between negative 1.5 and 0.5. Then, since we are finding probabilities using the CDF, we try to derive probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. Here, z is between two numbers. I write it as probability that z is less than 0.5. Z is less than a larger number. This inequality sign stays the same. This inequality sign stays the same. Minus probability that z is less than or equal to negative 1.5. This inequality sign will be switched. I will add equal sign under inequality. For this inequality sign, if there's no equal sign under inequality, add equal sign under inequality. But if there is equal sign, we remove the equal sign. So for the larger number, inequality sign stays the same. For the smaller numbers, inequality sign still points in the same direction, but add equal sign under inequality. That's phi of 0.5 minus phi of negative 1.5. Phi of 0.5. 0.50 is 0.69146. 0.69146. 0.69146 minus phi of negative 1.5. Negative 1.5 is here. 0 is here. I get 0.06681. 0.06681. If I subtract, I get 5, 6, 4, 2, 6. 0.62465. If I round to 4 decimal places, it will be 0.6247. Next example, in a city, the height of all male adults are approximately normally distributed, with the mean and the standard deviation of 176 cm and 8 cm respectively. When a man in the city is randomly chosen, find each of the following probabilities. Part A. What's the probability that the man's height is less than 180 cm? Part B. What's the probability that the man's height is more than 170 cm? Part C. What's the probability that the man's height is between 175 cm and 185 cm? So first step, let's decide what kind of probability distribution you want to use. Here, since a man is chosen from a normally distributed set, we can try to use normal distribution. Since a data value is chosen from a normally distributed set, we can try to use normal distribution. So let's set up a problem first. Let the random variable x represent the height of the chosen man. Then x has a normal distribution. X has a normal distribution. Mu is 176. Mu is the mean, 176. Sigma is A, so sigma square is 64. So for normal distribution, there are two parameters. First one is mu. Second one is sigma square. Be very careful. Sigma square. Sigma is the standard deviation. Sigma square is 64. Be very careful. Sigma is A. Sigma squared is 64. What we put here must be mu and sigma squared. Don't put A here. Don't put A here. What we put here must be sigma squared. So X has a normal distribution with mu equal to 176 and sigma squared equal to 64. Next, try to write down the probability density function of X. The PDF. For normal distribution, the PDF is 1 over radical 2 pi times sigma times e to the power of negative x minus mu square over 2 times sigma square, where s can be any real number from negative infinity to infinity. Sigma is A. Sigma squared is 64. Sigma is A. Sigma is A. So put A here. I get 1 over A times square root of 2 pi. Mu is 176. Put it here. Sigma squared is 64. 2 times 64 is 128. So here I get e to the power of negative x minus 176 square over 2 times sigma squared, that's 128. That's the PDF, probability density function. Then the support. For normal distribution, support of x is always from negative infinity to infinity. All real numbers from negative infinity to infinity. But let me say this. For normal distribution, since we are finding probability using a standard normal CDF, this is not necessary. For normal distribution, since we are finding the probability using the standard normal CDF, this is not necessary. All we need is write down what's mu, what's sigma. Since we are finding probability using the standard normal CDF, all we need is mu and sigma. Mu is 176. Sigma is A. That's all we need. So this part is not necessary. For normal distribution, since we are finding probability using the standard normal CDF, this part is not necessary. All we need is write down mu and sigma. Now, let's answer the question based on mu and sigma. Let's answer this question based on mu and sigma. Part A. What's the probability that the man's height is less than 180 centimeters? What's the probability that x is less than 180? The man's height is less than 180 centimeters. Since x has a normal distribution, we try to convert x to the standard normal distribution, then find the probability using the standard normal CDF. So convert x to z. The formula is z equal to s minus mu over sigma. Mu is 176. Sigma is A. So we have 180 minus mu over sigma. Then use calculator. 180 minus 176 is 4. 4 over 8 is 0.5. Then find the probability that z is less than 0.5. Since we are finding probability using the CDF, we know that probability of z less or equal to some number is phi of the number, and probability that z less than a number, is phi of the number. Here we have probability of z less than 0.5. That's in this form. So we have phi of 0.5. Phi of 0.5. Look at the table. 0.5 is here. 0.050. We get 0.69146. 0.69146. Then round to 4 decimal places. I have 0.6915. Part B. What's the probability that the man's height is more than 170 centimeter? What's the probability that the man's height is more than 170 centimeter? What's the probability that the man's height is more than 170 centimeter? Since x has a normal distribution, we try to convert x to the standard normal distribution first, then find the probabilities using the standard normal CDF. Convert x to z first. Take 170 minus mu, mu is 176, divide by sigma, sigma is a. 170 minus 176 is negative 6. Negative 6 divided by a is negative 0.75. Since we are finding probability using the CDF, I try to write probability in the form of probability of z less or equal to some constant, or probability of z less than some constant. Here we have probability of z greater than some number, so I try to use the complement. It can be rewritten as 1 minus probability that z is less or equal to negative 0.75. Then that's in the form of probability of z less or equal to some number. That's phi of that number here. So that's phi of negative 0.75. Phi of negative 0.75. Here we use a table. Negative 0.7 is here. Negative 0.7. 0.5 is here. 0.05 is here. Here I get 0.22663. I get 0.22663. 1 minus 0.22663. If we subtract, we get 0.77337. Then, if I want to answer to 4 decimal places, I get 0.7734. If we want to answer to 4 decimal places, we get 0.7734. That's part B. Part C. What's the probability that the man's height is between 175 centimeter and 185 centimeter? Part C. We're looking for a probability that the man's height is between 175 centimeter and 185 centimeter. Since x has a normal distribution, we try to convert x to the standard normal distribution first, then find a probability using the standard CDF. So convert x to z first. The formula is x minus mu over sigma. X minus mu over sigma. Then find z. 175 minus 176 is negative 1. Negative 1 over a is negative 0.125. (185) minus 176 over a. 185 minus 176 is 9. 9 over a is 1.125. Next, since we are finding probabilities using the standard normal CDF, I try to rewrite probabilities in the form of probability that z less or equal to some number, or probability that z less than some number. So here, this probability can be rewritten as probability that z less than 1.125 minus probability that z less than or equal to negative 0.125. Z less than 1.125. This inequality sign stays the same. For the other inequality sign, if there's no equal sign under inequality, add equal sign under inequality. Then that's in the form of probability that z less or equal to some number, or probability that z less than some number. I think this function, I think it's phi function here. That's phi of 1.125. This is phi of negative 0.125. Now, how do we find phi of 1.125? In the table, the first two digits is 1.1. second digit is 2. What should we do with this 5 here? Now, in general, if the third digit is 3, if the third digit is 0, the third digit could be 1, 2, 3, 4, 5, 6, 7, 8, or 9. The third digit here could be 1, 2, 3, 4, 5, 6, 7, 8, 9. In general, if the third digit is 1, 2, 3, round down to 1.12. If the third digit is 7, 8, 9, round up to 1.13. If the third digit is 4, 5, 6, we take the average between phi of 1.12 and phi of 1.13. If the third digit is 1, 2, 3, we round down to phi of 1.12, round down. If the third digit is 7, 8, 9, round up. So round down, round up. If the third digit is 7, 8, 9, round up to 1.13. But if the third digit here is 4, 5, or 6, take an average. If the third digit is 1, 2, 3, round down to phi of 1.12. If the third digit is 7, 8, 9, round up to 1.5 of 1.13. But if the third digit is 4, 5, or 6, take the average. Then it's find phi of 1.12, then find phi of 1.13, adding up, divide by 2. So phi of 1 here, the third digit is phi. So take average. The third digit is number phi. We take average. We find phi of 1.12 and phi of 1.13, adding up and divide by 2. Phi of 1.12 is here. 1.12 is here, which is 0.86864. Phi of 1.13 is the next number. 1.13 is 0.87076. 0.87076. Adding up, divide by 2. In my calculator, I get 0.8697. In my calculator, I get 0.8697. So phi of 1.125 is 0.8697. Now, next, phi of negative 0.125. Negative 0.125. So the third digit here is phi. We take an average. We need to find phi of negative 0.12 and phi of negative 0.13. Adding up, take average. Phi of negative 0.12. Negative 0.1 is here. Negative 0.12. Negative 0.12 is 0.45224. 0.45224. Next, find phi of negative 0.13. 0.13 is here. 0.44828. 0.44828. Adding up, divide by 2. Adding up, divide by 2. Here I use my calculator. I get 0.45026. Adding up, divide by 2. I get 0.45026. 0.45026. Then subtract. 0.8697 minus 0.45026. I get 0.41944. If we round the answer to 4 decimal places, it will be 0.4194. If we round the answer to 4 decimal places, it will be 0.4194. So for 5 functions, if the value contains more than 2 digits, look in the third digit. Round to the third decimal places. For five functions, if the value contains more than 2 digits, round to 3 decimal places. Look at the third digit. If the third digit is 1, 2, 3, round down. If the third digit is 7, 8, 9, round up. If the third digit is 4, 5, or 6, find an average between these two numbers, 1.12, 1.13. Next example, based on the previous problem, answer each of the following questions. Part A, what's the cutoff for the shortest 10% man in the city? Part B, what's the cutoff for the tallest 15% man in the city? Part C, what's the range for the middle 12% man in the city? So let's answer this question based on the previous problem. Answer this question based on the previous question. The X represents the height of the man in the city. Then X has a normal distribution with mu equal to 176. Sigma squared is A squared. Mu equal to 176. Sigma equal to A. Part A. What's the cutoff for the shortest 10% man in the city? We know that if the data set is normally distributed, it has an approximately bell-shaped curve. The distribution looks like upside-down bell shape. We're looking for the cutoff for the shortest 10% man. Suppose the cutoff is here. This part represents the shortest 10%. Suppose the cutoff is here. This part represents the shortest 10%. Assume this is G. If this is G, then probability that in a standard normal distribution, probability that G less or equal to G is 10%. Probability that G less than G is 10%. G less than G, that's 5 of G. 10% is 0.10000. We can try to find G in the table. Let's find the closest number to 0.1000 in the table. Let's find the closest number to 0.1000 in the table. In the table, the closest number to 0.10000 is this number here, 0.10027. This number is closer than this number, so we use this number. That's the closest number to 0.10000. This number, if I read the G value for this number, G is negative 1.28. If I read the G value, that's negative 1.28. Then we can convert G back to X. The conversion formula is G equal to X minus mu over sigma. If I try to convert back, S can be written as mu plus G times sigma. If I try to convert back, I can get S by itself. S equal to mu plus Z times sigma. So if I try to find X is Z mu plus Z times sigma. Mu plus Z times sigma. Z is negative 1.28. Here, this Z here is negative 1.28. If I try to find a corresponding X here, if I try to find a corresponding X here, if I try to find the probability that X is less or equal to X, equal to 10%, my X will be mu plus Z times sigma, which is, in my calculator, I get 165.76 centimeter. That means that's the cutoff of the shortest 10% man. If a man's height is below 165.76 centimeter, this man belongs to the shortest 10% man in the city. That's part A. Part B. What is the cutoff for the tallest 15% man in the city? What is the cutoff for the tallest 15 men in the city? So similarly, for the tallest 15 men, since the data set, the men's height are normally distributed, the distribution of the height has approximately normal distribution. The distribution has an upside down bell-shaped curve. The tallest 15%, assume that's Z here. That's the tallest 15%. So we're looking for the probability that Z greater or equal to Z equal to 15%. Probability that Z greater or equal to Z equal to 15%. But since we try to use the phi function, we try to use the complement. Since we try to use the phi function, we try to put it in the form of probability that Z less or equal to some number, or probability that Z less or equal to some number. So we try to use the complement. If I use the complement, I know that 1 minus probability of Z less than Z equal to 15%. So probability that Z less than Z is 85%. This is phi of Z. 85% is 0.85000 in it. 85% is 0.85000. Let's try to find the closest number to 0.8500 in the 85000 in the table. 0.85000, the closest number here is 0.85083. 0.85083. The Z value here, the Z value is 1.04. The Z value is 1.04. Z is approximately 1.04. But we are looking for the X value in general. We are looking for the S value. What's the S value here? We're actually looking for probability that X greater than X equal to 15%. We are actually looking for probability that X is greater than X equal to 15%. What's X here? For the corresponding X, use the formula that S equal to mu plus Z times sigma. So S equal to mu 176 plus Z times sigma. Then use my calculator, I get 184.32 centimeter. That means if a man's height is more than 184.32 centimeter, this man belongs to the tallest 15%. This man belongs to the tallest 15% man in the city. If a man's height is above 184.32 centimeter, this man's height belong to the tallest 15% men in the city. That's part B. Part C. What is the range for the middle 12% men in the city? How is middle 12% looks like? Middle 12%. If there are 12% in the middle, how many percent here? How many percent here? If there are 12% in the middle, how many percent here? How many percent here? They are totally 100%. 100 take away 12 is 88%. There are 88% left. 88% divided by 2 is 44. So we have 44% here. 44% here. We have 44% here. 44% here. Let me call this value Z1. Let me call this value Z2. Probability that Z is below Z1. Probability that Z below Z1 is 44%. And probability that Z above Z2. Probability that Z above Z2 is also 44%. Or if probability that Z above Z2 is 44%, then Z below Z2 will be 56%. 44 plus 12 is 56. Put in this form is easier. Probability that Z below Z2 is 56%. That's phi of Z2. That's phi of Z1. (44% is 0.44000). This is phi of Z2. 56% is 0.56000. Then find the Z1 and Z2 in the table. From the Z1 and Z2 in the table. 0.44000. The closest number, 0.44000. The closest number is here, 0.44038. That's the closest number. The Z value here is negative 0.1, go up, 5. Negative 0.15. The other one. Find the closest number to 0.56000. In the table, the closest number is 0.55962. The corresponding Z value is 0.15. 0.15. So Z2 is 0.15. Next, we need to convert Z back to X. The formula is X equal to mu plus Z times sigma. So S1 is mu 176 plus Z times sigma. I use my calculator. Here I get 174.8. For X2, I get 176 plus Z, mu plus Z times sigma. And I use my calculator, I get 177.2. That means if the man's height is between 174.8 and 177.2 centimeter, this man belongs to the middle 12% of the men in the city. So the range is So the range is the interval from 174.8 centimeter to 177.2 centimeter. If a man's height is between 174.8 centimeter and 177.2 centimeter, this man belongs to the middle 12% of the men.